All right, related rates. Related rates problems are applications of implicit differentiation. That's why I only needed to do one, because every related rates problem is an implicit differentiation problem. So there's built-in practice. Often we are finding the rate of something with respect to time. So it's often d dt that we're looking for most of the time. Example 1. Suppose y equals 5x squared minus 6x plus 2. Find dy dt when x equals 4, given that dx dt equals 2 when x equals 4. There's numbers everywhere on this thing. Job 1 is find dy dt. So I need to take the derivative with respect to t of both sides of that equation. So kind of showing what I'm about to do. Take the derivative with respect to t. So the derivative of y with respect to t is dy dt. What about the derivative of 5x squared with respect to t?
10x dx dt?
So 10x, power rule, but then chain rule dx dt. And then same thing with a minus 6x. Minus 6 dx dt. Plus 0, yeah. Find dy dt when x equals 4, given that dx dt equals 2 when x equals 4. Okay, so it gives me x and it gives me dx dt. So I think this is just plug it in here. X is 4, dx dt is 2. And not feeling like continuing on, you can be done, right? Like safe stop.
What's the multiple choice of it?
80 minus 12 would be 68. What I should have put on there is this sort of evaluation bar. I don't know if it has a fancy name or not. But if you put a bar there and write x equals 4, that says I'm telling you dy dt when x equals 4. So an important part of communicating your answer. Because without that, dy dt does not equal 68. dy dt equals all of this. dy dt at x equals 4 is 68. So make sure you communicate, when you're plugging something in. All right, so that one was pretty straightforward. No units, no geometry formulas, just here's the equation, take a derivative, plug in what we give you. That's about as simple as we can make the related rates problems. Number 2. Pebble is dropped into a calm pond, causing ripples in the shape of concentric circles. The radius of the outer ripple is increasing at a constant rate of 1 foot per second. When the radius is 4 feet, find the rate at which the area of that circle is changing. It's like words everywhere.
Translate it into calculus, please.
Yes, we need to translate, is right. The radius of the outer ripple is increasing at a constant rate of 1 foot per second. So something is 1 foot per second. That much I can get. The radius is increasing at a constant rate. So do you know how to translate the radius is increasing at a rate? So that's not r equals 1. It's how r is changing.
dr dt?
So dr dt. It's how r is changing, so dr dt. So dr dt is 1. When the radius is 4, so r equals 4, find, so what we're looking for, the rate at which the area is changing. So rate, that's a dead giveaway that something is dt, because it's a rate, the change in time. Change in time. So what are we looking for? The ADT, the change in area with respect to time. So they gave me dRdt, they gave me R, and they asked for dAdt. If only I had some equation that related some of those variables.
I feel like you're going to tell us how to translate that.
Well, I feel like the circles and area of a circle
Pi r squared?
is pi r squared.
Yay.
Like if it's a complicated formula, they'll give it to you. Like number 3, you can just glance down at example 3 and it tells you the volume. But easy ones, a lot of the times we don't give it to you. We expect you to know the area of a circle. All right, dAdt means I need to take the derivative with respect to time of both sides, because that will make dAdt show up. I think I'm going to press pause and see if you can finish this one. So dAdt on the left, derivative with chain rule on the right, plug in your pieces, say stop it if you want to.
Dang.
Well, we can also check the other side, because the other side was 2 pi, and then the radius was 4 feet, and dRdt was 1 foot per second.
Yeah, feet squared.
So yes, 8 pi, but you can also look at the units in there and see feet squared per second. So the easier way is to just get it from what it's asked. If you get it from what it's asked, you can get the answer, you can get the unit without even getting the answer, right? Because dAdt has to be feet squared per second. So, and a lot of times on the AP test, they assign a point to the unit. And so even if you see dAdt, and so you know that's going to be feet squared per second, if you completely mess it up the rest of the way, you're going to get that point for a unit because you knew what they were asking for and what the units would be. So it's a good question. If it's not asked for, it's not graded. In here, I'll try to always ask for it because I want you to get used to doing it. But on the AP test, if it doesn't specifically say what are the units, then they're not really even looking for it. Number 3. Water runs out of a conical tank at a rate of 2 cubic feet per minute. Now let's just read the whole question, then we'll go back and translate. The radius at the top of the tank is 5 feet, and the height of the tank is 10 feet. How fast is the water level decreasing when the water is 4 feet deep? The volume of a cylinder is given. Okay, so first, probably helpful to picture what's going on. So there's my conical tank. There's like a hole at the bottom, so water's pouring out of that cone. Something's happening at a rate of 2 feet cubed per minute. Now, speaking of units, you can read the words and figure out what variable goes with that. Sometimes you can just look at the units and figure out what the variable is. Feet cubed per minute. Well, let's go with what the words say, because that's probably the safer bet. Water runs out of a conical tank at a constant rate. There's your hint that it's something dt. Of 2 cubic feet per minute. So the change in time is in minutes. What is feet cubed measuring?
Volume.
That would be volume. Something cubic is volume. So dV dt is 2 feet cubed per minute. In fact, that's not exactly right, though. Let's see if I can convince you what's going on. So there's water in there. It's running out. So the change in volume is negative 2 feet cubed per minute because you're losing volume. So that's kind of tricky because they don't always tell you that it's negative. You have to read the words carefully. It's running out of the tank. So the volume is getting less. So its change is negative. It's decreasing. Let's see. The radius at the top is 5. The height is 10. Do something with that in a minute. How fast is the water level decreasing when the water is 4 feet deep? So when h equals 4, find, what are we trying to find in terms of variables? Not dV dt, because the h dt, how fast is the water level, how fast is the height decreasing? We know what dV dt is. What we're trying to find is dH dt. So V equals 1/3 pi r squared h. Okay, slow down. Don't take a derivative of that yet. Because if we take a derivative of it now, we'd have to use the product rule. Which we could do, but then dr dt is showing up, dH dt is showing up. We want dH dt to show up, but I don't really know anything about dr dt. So I'd really like to get rid of the r. Like, we prefer only 2 variables. Like strongly prefer. Like, sometimes we can't get away from it. We'll see some questions where you're just stuck. But man, if there's something that we could get away from having R and H in there, that would be fantastic. If there was some relationship between R and H. Look over here at our picture. It would be great if I knew R in terms of H. Actually, the other way around, no, that's the way I want, because I want to get rid of R.
So you solve for it?
So that ratio, because it's like similar triangles all the way down, 2 to 1 or 1 to 2, depending on how we want to say this. R is, let's see, always half of H. That's why they gave us the 5 and the 10. R is half of H. So even when we're down here toward the bottom, R is still half of H. So that means I can get rid of R and put in half of H. Adds an extra fraction, but I'm happy to pay the fraction price to avoid the product rule price. So let's see, that's 1/12 now. 2 squared is 4 times pi times h cubed. Yes. So you prefer, if possible, to have 2 variables rather than 3 variables, then take the derivative. So we paid a little bit of price in algebra, but more than worth it to avoid the calculus price we were about to have to pay. And by the way, we still would have had algebra to go, because if we did the product rule up here, dr dt was going to show up.
Yeah.
And I don't have any dr dt information, so we needed to make that change. Okay, so dv dt then is 3/12 or 1/4 pi h squared. Why is that incomplete? What's not right?
Times, yeah, DHT.
Time dHdt. So the chain rule, times dHdt. Okay, so it said we're trying to find dHdt. Okay, do we have the other pieces of this?
This?
Do we have dV dt?
Yeah.
Yes. Do we have h?
Yes.
Yep. So we're ready to go. dV dt is -2 pi over 4. H is 4. Do you know if that's a safe stop?
No.
Why not?
Because dHdt isn't on its own.
Right, you haven't solved for dHdt yet. So you can leave, algebra stuff left to do, or computation stuff left to do, but you haven't answered the question yet. Find dHdt. So let's see. -2 equals 4 pi. So dHdt then is -2 over 4 pi. That's a safe stop. It also simplifies, but it is a safe stop. -1 over 2 pi. It didn't ask for units, but what would the units be? What's the units of h? Feet. Not feet squared, but feet. And time in this problem, everything's in minutes. So feet per minute. So we just found out how quickly the height level is going down based on how fast the water is flowing out of the tank. That gets to be a tricky one because of the two variable thing. Okay, let's do. You'll have to, if I give you a two variable thing, then you have to find some relationship between the two variables so that it's not three variables, it turns into two variables. My face in the way. Yes, so you can product rule that, but if you do, you're going to end up with somewhere you're going to have dr dt,
Right.
and we don't have any information about dr dt.
Right.
So eventually, I almost want to hit pause because this is a terrible way to work this problem, but you could get dr dt, but you would have to have this equation, which means you still need that equation. Because you could take the derivative of both sides of this equation to find dr dt in terms of dHdt, and then plug it in. Let's do the algebra up front.
Yeah.
So it can be done, but it's just much better. That's what I said, prefer. It should be strongly prefer. We only want two variables, especially if product rule is involved, because you're going to have ddt's all over the place if you don't make that switch. Number 13, a 13-foot ladder. Number 4, classic problem. Haven't made the test yet, but just about guaranteed that this type of problem will be on there because this is in every calculus book ever written. Maybe not ever written, but
this exact problem?
This type of problem. A 13-foot ladder is leaning against a wall. Picture time, for sure.
It is a triangle.
It is. Now, this may seem simple, or maybe it's complicated. I don't know. But where does the 13 go?
Hypotenuse.
That's hypotenuse, because the ladder is 13 feet tall. So make sure you put 13 on the ladder.
Could you just use Pythagorean theorem?
We're going to use Pythagorean theorem in a minute. Suppose that the base of the ladder slides away from the wall. Uh-oh, so this is not good if you're standing on it.
Yeah.
Sliding out at 3 feet per second. Don't really have a variable for that yet, so we may need to introduce some. How fast is the top of the ladder sliding down the wall? Okay, that makes sense. The bottom is sliding out, the top is sliding down. How fast is the top of the ladder sliding down the wall when the base of the ladder is 5 feet from the wall? Indicate units of measure. So we do want units on this one. Okay, you said Pythagorean theorem.
Yeah.
Why did you say that?
Because you can figure out what y is. You just won't know what dy dt is.
Okay. So do you want to use, you said y, so do you want to call this side y?
Yeah, because that's height.
Right. Then this side would be x. If you used a and b and c, that's completely okay too. So now we can know what exactly this 3 feet per second is in terms of the variables we have.
dx dt.
That's how x is changing. That's dx dt. X is growing, so dx dt is positive 3 feet per second.
But since the ladder's falling, would it be a negative dy dt then?
Well, it should be. We should get a negative answer. And that is at least a small check on almost all of these word problems, is that you'll know if you got at least the sign right.
Yeah.
Because if they're both getting bigger, then, I guess you could have one of those extendo ladder things, but that's not what's happening here. What are we trying to find in terms of our picture?
dy dt.
dy dt. When the base of the ladder is 5 feet from the wall. So what's 5?
X.
When x is 5. So find dy dt when x is 5. And we know dx dt. So you've sort of already mentioned the equation that governs this. X squared plus y squared equals 13 squared. Although that mistake would be common, but also erased here when we take a derivative, because derivative of a constant is going to go away. I'm trying to find dy dt, so I need to take the derivative of everybody with respect to time. So the derivative, I should find some popsicle sticks now. Add to the fun. Got people dropping here. Got to find the people who haven't dropped. There's a team of all-stars right there. Haven, what's the derivative of x squared with respect to t?
2x. Is it dx or dt?
Yes, good. Now, if Julia can't follow your lead after you did that one, Julia, what's the derivative with respect to t of y squared?
2y dy.
Very nice. Mia, how about the derivative of 13 squared? Oh, I thought I gave you the easy one.
Is it 0?
It's 0. Why is it 0? Don't know? 13 squared is a constant.
Yeah, but it has the square.
It has a squared. Okay, if you want to take the squared thing, so you want to do the power rule on that. So 2 times 13 to the first times the derivative of 13 with respect to t.
That'll just be 0.
That would be 0. So yeah, you can still use the power rule, but it would be much better if you just said, wait a minute, that's a constant. Constants don't change. That's why they're called constant. So their derivative is 0.
When constants start changing, that's when we need to
Yeah,
worry.
something's going on. Okay, now do we have all of our pieces here?
Yeah.
Let's Let's see. I'm going to divide by 2 just to get rid of the 2. And we're trying to find dy dt. So let's plug in the things that we know. X is 5. Dx dt is 3. I don't know why.
Well, you could solve with Pythagorean.
Yeah, but I could know why. When x is 5, y would be 12. The old 5, 12, 13 triangle.
Or you could just work it out.
Or you could work it out. But a lot of times they give you ones that are Pythagorean triples so that things are nice.
I couldn't remember my Pythagorean triples, so I had to work it.
Be careful with labeling these as 5 and 12, because if you label them too early, then you start to think they're constant. It's like, oh, that's 5 and that's 12. Like, no, that's changing. At an instant it's 5, at an instant it's 12. So be careful what you label. If you label it, you're telling me that that's 13 always. And that is 13 always. Like, this thing starts sliding down, but it's still 13. X and y are changing, 13 is not. Okay, so dy dt would be negative 15 over 12, which is a safe stop. See if I can not mess this up. Divide both by 3.
5 over 4.
I said divide by 3, and then I didn't do it right. Negative 5 over 4. That is why we safe stop, to avoid
But there's units.
taxing your brain.
Units.
What's that? Because when I moved the 15 over, I subtracted it over. So, okay, hold on. There's like 4 questions I got to answer. Did you figure out where the 2 went?
No. I think I got it.
The 2 went. I just divided everything by 2 to get rid of it,
Okay.
since zero is on the other side. Why is it negative?
Because you moved the 15 down.
It's going down. So that makes sense. Again, a lot of times, based on the problem, it'll make sense if the pile of rocks is getting bigger or the circle's getting smaller. Like, you can figure out if it's supposed to be positive or negative. And then it does say units, so I can put units on all this and try to solve with the units, but it's probably better to just look at dy and dt. The units of y is feet, and the units of t is seconds, so feet per second. Okay, let's stop there. The next one is an angle problem, so we get into trig stuff.
Yay.
Don't do that yet.
Unless you're in physics on ramps.
So I would say on worksheet 2, I'd say 1 through 12. And by the way, some of 1 through 12, like, look at number 3. Oh, that's not the one I wanted to look at. Some of these are not even, there's not really even math to do. They're more like translation problems.
Hey, number 9 is something we did already.
Yeah, we got. Yeah. So 1 through 12 roughly coincides to what we did today. Plus, I wanted to just split it up half and half. So try some from 1 through 12. I'll answer those on Thursday, and then we'll work some more from 13 to 24. So nothing new on Thursday. Well, kind of new.
A couple.
I mean, nothing new in theory, but we just hadn't done an angle problem yet.
Yeah, but we all took
And the
geometry.
shadow problems are also fun.